Yes, Kenneth.
Thank you, Tim, for that introduction, and also welcome from my side. I will talk a bit about our experience with AlphaFold in the last couple of months in terms of installing it and in terms of some important performance aspects in the sense of speed, so how quickly you can get AlphaFold to run. So this presentation was put together by myself, but with a lot of help from the various people you see on the slide. The different HPC hubs within the Flemish Supercomputing Center, so VUB, Antwerp, Leuven, also some help from Tim himself, and a lot of help from Jasper from VIB as well. Okay. It's not. There we go. Okay, so the agenda is, well, AlphaFold in a nutshell, but I think we can mostly skip that part since I think it's very clear that everyone here knows about AlphaFold, what it does. We'll give a high-level overview of how AlphaFold works inside without going too technical. So I'm a computer scientist myself. I know what proteins are, but don't ask me too much about them because then I'll have difficulty answering your questions. But I do know a lot about the technical side of how AlphaFold is working, what it needs to get running, how you can get that working, and the important aspects there for in terms of performance, of how quick it runs. We'll take a look at the different versions of AlphaFold, how they are different, and how quickly they have been released, and the dependencies that are required to get AlphaFold running. And then looking into how you can install AlphaFold and two main alternatives there, and also the performance considerations that come with that, and also the different aspects that affect performance, like using CPUs, using GPUs, the I/O aspect, and so on. We also have a couple of slides on beyond AlphaFold, but I think that's mostly been covered in the discussion as well. And we'll wrap up with an overview of the VSC resources that are available for running AlphaFold. So yeah, proteins, I'm not going to spend any time here. I think it's pretty clear. Everybody knows what proteins are and why we want to predict their 3D structure. So we essentially start from a sequence of amino acids, letters as input into AlphaFold, and we want to get 3D structure, a prediction of the 3D structure out of that. If you're new to this, Jasper has given a very good talk on that's a bit more high level, and I would say easy to understand by computer scientists or system administrators at the EasyBuild user meeting a couple of weeks ago. So do check that out if you want to get the high level view on what AlphaFold does and why that's important. Also here, I guess this is not news to anyone, but AlphaFold is creating a bit of a revolution in protein structure prediction. It has done that through this CASP competition where it vastly outperformed any previous methods. Certainly with AlphaFold 2, there was a very good result there, and it essentially accurately predicts the structure of proteins with some caveats, of course. And yeah, living up to the hype, so there was a lot of noise about that AlphaFold is a solution to a 50-year-old grant challenge in biology. That's a very strong statement. But at least it indeed has lived up to some of that hype in terms of results. When we look at the version history, it all really started with AlphaFold winning the CASP 14 back in 2020, so the end of 2020. It took a while before it actually became publicly available. So the publication in Nature happened in July 21, and then the actual code and the protein structure database became available in shortly after, so the same month essentially. And in July, we started getting requests from scientists to install AlphaFold on our HPC resources. Now, this was a bit of a special case for us. So we get installation requests on a daily basis. In Ghent, for example, we get about 250 software installation requests a year. So we're quite used to this. But what we weren't used to is getting a request from multiple different research groups, 5, 6, 7, for the same software in the same week. So that has really never happened in the 10 years that I have been active in the HPC team in Ghent. So clearly something was going on there. This was a very important application that many people wanted to get their hands on and start playing with, start evaluating. So even though it happened over summer, where many of us take a long leave, by the end of the summer, we had AlphaFold working on our HPC infrastructure in Ghent, and then shortly after also in the other VSC hubs. So we were quite quick with getting this running and helping out the scientists who wanted to run this. And since then, it has evolved with the AlphaFold Multimer version, so AlphaFold 2.1, which has support for predicting protein complexes. And very recently, there was also a version 2.2 available, which has updated parameters for Multimer. And that's the one we're now actively looking into installing as well, and where we're running into some small issues with one of the dependencies. So we don't just install it and claim we're done. We also try to do a good job of making sure it's a high quality installation and that there's nothing wrong with all the components that are involved. So how does it actually work? The high level overview of AlphaFold 2, it actually consists of a sort of a three-step process, where the first step is the multiple sequence alignment, MSA, but it's looking for similar proteins compared to your input in a collection of databases, and it's basically picking things that are interesting or close enough to your input sequence. Then it uses this as an input for the actual structure prediction, which is the second step, where some pre-trained neural networks are being used to give a hopefully accurate prediction of the 3D structure of that protein. And then at the end, you can also do a relaxation on that structure, which is now optional since one of the recent versions of AlphaFold. To do all of this, it actually requires quite a bit of resources. So both in terms of storage, so the databases of proteins take up quite a bit of disk space, about 2.5 terabytes, roughly. So this is pretty much beyond what you can do on a regular laptop or regular workstation. So that's already an issue there. The process, especially the structure prediction part, and depending on what kind of resources you have, also the MSA part, is both pretty compute intensive. The MSA part specifically is also very IO intensive, so it's accessing all that data when doing the search for similar proteins. So depending on the resources you have available, you can get quite a bit of speed up for those AlphaFold runs, especially with GPUs and SSD disks. What's very nice about it is that it's available as open source software. So both the code itself and also the parameters for these pre-trained models, as has been mentioned, are now available under an open license. So they can be used by anyone, including the industry. This is a very detailed picture of how the three-step process works. I won't go into the details here. What's mostly important here, this is three big steps: MSA, prediction, and relaxation. And this is something that will pop up as well in the rest of the presentation when we start looking at actually benchmarking the performance of AlphaFold, how quickly it can do each of these steps. In terms of dependencies to get AlphaFold running, there's actually quite a bit of them. On the left, you see Python and all these different Python packages that AlphaFold needs, NumPy, SciPy, a whole bunch of them. So getting those installed and running, getting those installed correctly and running well can already be a bit of a challenge for some people. And then you're just getting started. Then you don't even have the MSA tools yet, like Hummer and 𝙬𝙧𝙎𝙧, or the TensorFlow and JAX software components that you need for the prediction step, and OpenMM for the relaxation. And then when hopefully you are using GPUs for running AlphaFold, then you have additional components like the CUDA library and these additional libraries that are available as well. So in terms of software stack, this is relatively big. And some of these components, in particular JAX, can be difficult to install if you want to do a good job of using the available resources in your system. So to get AlphaFold installed, there's two main options. The one obvious one is using container images. This is also what is basically provided by DeepMind. So in the GitHub repository of AlphaFold, you get a Docker file. You can use that to build your own container image for running AlphaFold and then run it like this. That's helpful. If you're a bit familiar with containers, you can probably get that done. if this is entirely new to you, this is already going to be a challenge. Now, there are pre-built container images available as well, for example, on Docker Hub. So I'm not sure who this person is or if they are a member of DeepMind at all, but you can basically get readily built container images for AlphaFold just straight from Docker Hub, download them and start running them. Or if you prefer using Singularity, so something that's more HPC friendly, a container runtime that you can use on HPC infrastructure, you can do it as well. And there's essentially copies of the Docker images available through Singularity as well. To run this, you use, for example, the Singularity command. You give it the AlphaFold container image, and then you specify what kind of command you want to run. And you basically just feed in your input sequence to do that. Now, the benefits of using containers is that it's pretty quick to install. I'm not sure if you can talk about installing if you're using a container image, but okay. Just downloading a pre-built container image and making sure it's available on your system and get started with that takes about 15 minutes. So if everything goes right, that's pretty quick. The downside of this is that you may actually not be fully using the resources that you have available in your system. And that's not because containers are bad or anything like this, or that there's overhead in using containers. That's usually not the case. But what's typically being done in a container image is that they include software binaries in there that work on a broad set of hardware. So that means the binaries are built in such a way that they can be run on a laptop or on a very expensive, very recent Intel processor, for example, which you may find in a supercomputer in an HPC system. That means it comes with a cost, and we'll quantify that cost a bit in one of the upcoming slides. So that's one aspect. Another aspect is that there may be trust issues with using a pre-built container image. Or just downloading something from Docker Hub and you don't really know who built this. Can you trust that person, or do they have something in that container image that you maybe don't want to run on your system? So that's an aspect you should take into account as well. Another option, and that's the option we are using in at least in Ghent and throughout most of the VSC, is to install AlphaFold and all the required dependencies from source code. So all the source code is available publicly, at least for most components. For things like the CUDA library, that's not the case. You have to install that just as a binary, but there's no other option there. So that's another way of installing it. This can be very time consuming and tedious, especially if you're not used to doing this. You may run into compiler errors and God knows what other problems when doing the installation. And because AlphaFold and everything it requires is not the only software we install on our HPC infrastructure, we actually install thousands of applications and libraries for all kinds of scientific domains. We've learned very quickly that we need to automate this and make this as easy as possible while still building from source code, because we don't want to pay that performance penalty that you could get when using pre-built binaries. So because of this, we've come up with a tool ourselves, which we have been developing for about 10 years, which is called EasyBuild. And that makes the installation of complex software like AlphaFold as easy as it can be when doing that from source. So the 4 commands that you see there on the slide is how to install EasyBuild itself, how to run EasyBuild, so the EB command to install AlphaFold and all its dependencies. And then when that is done, and this will take multiple hours, the second command to actually finish. When that is done, you get an AlphaFold module, an environment module that basically activates the software for using, and then you can go ahead and run AlphaFold. The last command is what we actually do as a part of EasyBuild as well, specifically for AlphaFold, is make things a bit more user-friendly. So traditionally in AlphaFold, you get a Python script that you use to drive your run. We've actually wrapped that in a nice AlphaFold command that is a bit easier to use. And you can set some environment variables as well to point to the location of the database, for example, so you don't have these huge command lines anymore. So things become a bit shorter and a bit more user-friendly without really changing anything to AlphaFold itself. So the benefit of doing an installation from source is that usually your AlphaFold installation can be significantly faster. Because it's just optimized for your specific hardware. If you have a very recent Intel processor, for example, and you want to use that to its full capacity, this type of installation will actually allow you to do that. The obvious downside is the installation process itself. takes a lot longer if everything goes well, and if you run into a problem, it may also be a bit more difficult to solve. But hopefully, EasyBuild takes care of most of that, and it's a one-time cost once the installation is done. Hopefully, that's no longer a problem. So to evaluate the performance of AlphaFold, both of how it was installed and also some other aspects, we've done some experiments in the last couple of weeks. All of these were done with AlphaFold 2.1.2, since 2.2 was released only very recently, and we were in the middle of this benchmarking effort. So we stuck to the version that was available when we started this exercise. To do this, Jasper actually has selected a set of input sequences with different lengths to get some variation in the input sequences and see also the effect of these lengths on the runtime. They're listed here on the slide. I won't go into details on this, but all of these sequences are available through the GitHub repository that's mentioned on the website. So vscentrum/VSC Alphafold. You can get all the sequences there and some scripts and things around that can help you with using those and doing some benchmarking of AlphaFold yourself. So we looked at different aspects of running AlphaFold using these sequences. One of the first things we did is just look at the impact of the runtime and also the different phases, the runtime of the different phases, depending on the length of the input sequence. And as you can see on the left, we have lengths of 200, 400, 600. So those are pretty quick to run. The black line shows the total runtime. So that's all well below 1 hour, at least if you have quite powerful resources. So this was run on one of the tier 2 HPC clusters in Ghent, where we have A100 NVIDIA GPUs, which are quite powerful. Actually, the most powerful GPUs you can buy nowadays, together with pretty recent AMD processors as well, AMD Milan CPU cores, and quite a bit of memory is available as well per GPU. So this is a significant amount of resources. And maybe the runtimes you're seeing here are a bit shorter than what you may expect, but that's just because we have a very powerful GPU available in this system. As you can see on the right, when you're looking at sequences of length rather big, 2000 amino acids, the runtimes, of course, start creeping up, and that's where you'll be spending lots of time. And also when you're looking at protein complexes, you can basically add up the length of your input proteins and get a similar result. So if the total length of all your input proteins combined is in this range, you'll probably get a similar runtime as well. And you can see that the biggest part of the runtime is dominated by the first two steps, the searching for proteins and the actual prediction itself. Then we also, or actually Jasper did also experiments on Google Colab, and compare this with the HPC resources we have in this particular cluster. And for a lot of these input sequences, especially the longer ones, you run into trouble quite quickly in terms of memory limits of the GPUs. So the GPUs that are available through Google Colab are also NVIDIA GPUs, but are way more basic GPUs, let's say. So definitely not as powerful as the A100s we have in this cluster in Ghent. So you quickly run into memory limits when using longer sequences, or even just timeouts. So you get a certain amount of time in Google Colab and pushing through all these 5 models or getting the predictions from all 5 models in the second step. Even with an input sequence of just 1,000 amino acids, you already get into trouble. And there's actually another aspect here. When using the HPC-UGent resources, we were using the full database, which is about 10 times bigger than the small database that is being used in Google Colab. So that's a very important aspect as well. You can't really compare the numbers that we're getting on the HPC and Google Colab directly, because you're using 10 times more data on the HPC system. So that's a very important thing to keep in mind here. But as you can see, you're hitting limits quite quickly in Google Colab, which you're not hitting with significantly more resources. Then another aspect is the GPUs. Do you really need GPUs to run AlphaFold? Well, yes, you do, if you want to do it in a reasonable amount of time. So the 2 left experiments were done on CPU-only clusters in the UGent HPC infrastructure. So the left bar is on Intel Skylake CPUs. Those are about, let's say, 3 to 4 years old. And then the AMD Rome system is a lot more recent, and you're getting slightly better performance there. So on the order of 2 hours for the shortest input sequence of length 200 that we have. But if you're using the GPU resources we have, so these powerful V100 or A100 GPUs, you're diving well below half an hour for these short sequences. So you're getting a speed up of about 5 times when using sufficiently powerful GPUs compared to only using CPUs. And as you can see, most of that is in the prediction part. The red part, the MSA part, is CPU only. Your GPUs are just waiting there for something to be done, so that they don't help you with the MSA part. But of course, with the prediction part, they are a big help. And also, in the latest versions of AlphaFold, in the relaxation part, they give a big speed up as well. This is with a very short sequence. If you look at a longer sequence, so the middle one of length 1000, then the speed up is even more apparent. So on the left, we'll see the CPU only clusters again, so the same two as in the previous one. And we're seeing runtimes of 15 up to 20 hours even, while on the GPUs we're well below 1.5 hours, or even on the powerful A100 GPUs, less than 1 hour. So we're getting a speed up of about 15 to 20 times faster. So rather than spending a day, you're spending about an hour or 2 hours to get the result out. So that's a big difference, and yeah, that of course enables you to do a lot more things. You're not only getting the results faster, we can do, let's say, 20 times the amount of work in a single day that you can do with only using CPUs. So that's a big difference, of course. Then another aspect is the location of the databases that are being used in the first step in the searching for sufficiently comparable proteins that are then used in the input for the prediction. So the red part of the graph, there's a big impact depending on the location of your database. So you better make sure that those databases are available on a fast file system. DeepMind recommends you to use SSDs, and there's a very good reason for that. So you can see on the left, we were not using SSDs. We were using one of the slower file systems that we have in the HPC-UGent infrastructure. It's a slow file system. It's still useful for certain things. We use this for long-term storage of data. So if you have big databases, terabytes of data, you can park them there. And whenever you want to actively use them, you can copy them from there to another faster file system. So at least they're already on the system. You don't need to upload all the data. But when actually actively using it for your research purposes, you should copy it to a faster file system. If you're not doing that and just ignoring that recommendation, you can see you're taking a performance hit of about 4 times faster than using the fast SSD-based file system. So that's a very big difference as well. For just the MSA step, you're getting a speed up of 4x. So that's quite significant. And even comparing with our regular fast file system, so our regular what we call scratch file system, compared to the ones we have with SSDs, there's another 50% speed up for the MSA part. So that's again a significant difference. So if you have SSDs available and there's enough volume available there to park all that data on, you should definitely use them. Then another aspect is how AlphaFold was installed. Again, containers versus from source installation, in this case using EasyBuild. So two different plots here on 2 different GPU clusters, one with V100 GPUs and A100 GPUs. So there's a big difference there in the in how fast these GPUs are and how much GPU memory is available on them. But there's an important difference in the CPUs as well. So remember the MSA part is being run CPU only. You cannot use GPUs to speed up that part. And there's a difference between Intel and AMD GPUs. Recent Intel GPUs have support for a particular type of what's called vector instructions that are 512 bits wide. So this AVX512 instructions, which are a significant help for speeding up the MSA part. But when you're using a container image, you're using binaries that do not use these instructions at all. So do not use that part of the CPU. And then again, you're taking a big performance hit by not properly using the capacity or the what your CPUs have to offer. So you can see the difference in the red part for the container and the EasyBuild installation. If you're doing a proper from source installation, of AlphaFold, and then you're indeed using those Intel CPUs to their full capacity, you're getting about a 20% speed up of your total runtime. So that's again significant. If you're only doing one run and it finishes in 4 hours rather than 5 hours, maybe you don't care too much. If you're doing 100 or 1,000 runs, a speed up of 20% is quite significant, of course. On the AMD Rome system, we were seeing a speed up as well of about 12%. The impact there is bigger because there the difference between not using these AVX512 capabilities of your CPUs or not using them is a bit smaller. But on modern CPUs, you should really be careful when using container images for long runs. Then beyond AlphaFold, some of this has already been discussed. There's RosettaFold, which is sort of a direct competitor to AlphaFold with similar ideas. There's ColabFold, which takes a slightly different approach, especially for the MSA part. And then there's OpenFold as well, which is it looks very interesting to me, but it seems like not too many people have played with this already. And there's probably a reason for that, which I'll get into in that specific slide. So you can see it's not just AlphaFold anymore. This field is opening up really, and there's multiple software applications like this that sort of take this AI-based approach to protein structure prediction. So just stepping through them one by one, ColabFold gives you a bit more customizability, especially the MSA part is quite different. So they're using different software. They're not using 𝙬𝙦𝙦𝙬𝙤𝙬𝙬𝙬𝙬𝙬𝙬𝙬𝙬, but they're using MM62. And they actually, in ColabFold itself, so in the notebooks you can get access to, they're using a dedicated web server as well. So whenever you're giving it an input sequence and it has seen that before, it will just straight give you the answer. So in less than a minute, you will get the result of your MSA search rather than actually doing the search. So this is a big speed up, of course. And you can do this local installation as well. So pull all those databases locally and use MM62 through the ColabFold software to get something similar. Now, the difference with an on-site installation on an HPC system like ours is that even though ColabFold is a lot quicker for the MSA part, it's still a lot slower for the prediction part since it doesn't have these powerful GPUs available. And you can probably make the best of both worlds there by doing a local installation of ColabFold with MM62 and this, which does this database or this quicker search through this index. But again, this is something to keep in mind. RosettaFold is then, of course, a bit different. So a similar approach, which was developed sort of concurrently with AlphaFold from a different lab. They were second in this competition, and now they've made quite a bit of improvements based on what AlphaFold has done recently as well. It's available on GitHub, but there's some licensing constraints as well, which was also mentioned before. So that's certainly something to be aware of at least. And then there's also OpenFold. This looks very promising, but also very challenging. So it's in essence a re-implementation of AlphaFold using PyTorch rather than TensorFlow. So PyTorch is becoming quickly more popular than TensorFlow is in the AI community. So that's already an interesting aspect. But what's also interesting is that this allows you to train your own neural networks, train your own models rather than using the pre-trained models that come with AlphaFold. The downside of that is this is very, very compute intensive. So on the AlphaFold website, they mentioned that to obtain these pre-trained models, they were running on about 100 GPUs for weeks. So you can imagine if you want to train your own models, you would need quite a bit of time to actually do that and get some good results. But again, at least the possibilities are there. And as far as I know, OpenFold is also fully open source and available to anyone to use. And to wrap up, the HPC resources we have available in the Flemish Supercomputing Center at the different hubs. So in Ghent, we have 2 GPU clusters, one with V100s, one with A100s. And we have a fast scratch file system, which is powered by SSDs as well, which is a significant benefit. And also in the VUB, they have a GPU system available, one with slightly older GPUs, P100 GPUs, so which are, I guess, a bit less powerful, but definitely still useful for AlphaFold, and you'll still see big speed ups compared to using only CPUs. And also some A100 GPUs are available there. And Leuven, they were an early adopter of GPUs and making those available to researchers. So they have quite a bit of P100s available. and also limited amount of V100s. And I guess they're in the process of also making A100 GPUs available. And then on the tier 1 cluster, so this is, let's say, a step up within the VSC. So the tier 1 is one big system that is shared across all Flemish researchers and industry. So there also we have a significant GPU partition. And one benefit there is that the waiting time to actually get access to these resources is a lot lower, because there's a lot less researchers active on the system, because they need an approved research project before they can actually get access to this particular system. For industry, it doesn't really matter. If you have a contract and you're paying for the resources you use, you can get direct access to Hortense as well. Then going beyond the VSC, there's also, let's say, on the horizon in the European context, significantly more resources available that could be used for running AlphaFold or any of these AI-based structure prediction applications. LUMI is currently being installed in Finland. For now, it's only the CPU partition, but the GPU partition is coming together, and they have dedicated storage as well, fast systems with very fast I/O, which will be very helpful for things like AlphaFold as well. So that this is something to keep an eye out for, and in the near future, this will also be available to Belgian researchers and industry. And then to wrap up, so these AlphaFold community sessions, today is the first one. Our goals for this are to try and bring different parties, both academia and industry, together who are interested in AlphaFold, and it seems like, at least for this first session, that has been quite successful. We want to facilitate exchanging of ideas and experiences, both specifically to AlphaFold and also beyond that, and also sharing some of the expertise, both in terms of the research, but also on using AlphaFold and making sure you do this in a good way to get the result as fast as possible. We hope to do multiple of these sessions per year. We actually have our second session already planned. So at the end of April, Jasper and Alexander will do a 2-day training session on protein structure analysis and AlphaFold specifically. And this will include some hands-on exercises with AlphaFold on the VSC HPC infrastructure as well. So the website is mentioned here on the slides. And there's you can contact him directly at FWO if you actually want to attend this second session free of cost as well. So there's some cost implied, but for the people active in this AlphaFold community, FWO is willing to cover those costs. And that wraps up the slides I had. There's a couple more resources here to look into, like our GitHub repository with these input sequences that we used for the benchmarking, Jasper's talk, high-level talk on AlphaFold at the EasyBuild user meeting, and also the AlphaFold course that's available that you can just click through at your own pace to get started with AlphaFold on the VSC resources, and then some general information on the Flemish Supercomputing Center as well. I'm happy to answer any questions if there are any.